Okay, we're going to start chapter 16 now, and chapter 16 deals with special solutions. They're called acids and bases, and I'm sure you guys have heard of them before. Most people think of acids as this nasty stuff that burns through your skin, and they use it to torture people, and some of them could do that, I guess. But a base is the opposite of an acid, but it could do the same thing. But you don't see anybody dropping bases down and, eating away somebody's flesh. It's kind of a movie thing. Okay. All right, so some of the definitions, so we know what an acid is. An acid, there's three different guys that worked with it. One of them was named Arrhenius. It was a Swedish guy. There was another guy, there's Lewis, which we've talked about Lewis structures. He did a lot with chemistry. And then there's another guy called Bronsted, okay? So Arrhenius, he said an acid is a substance that when you dissolve it in water, increases the concentration of hydrogen ions, okay? And it's easy to tell if a substance is an acid. If hydrogen is listed first, it's an acid. It's that simple. If you think about it, HCl is hydrochloric acid, H2SO4 is sulfuric acid. So if hydrogen's listed first, and that's the most traditional of all the definitions. For a base, what Arrhenius said is it's a substance when dissolved in water increases the concentration of hydroxide. Remember, hydroxide is OH. So if you think about water, water is HOH. So if you dissolve something in water and you get more H's than OH's, it's an acid. If you get more OH's, if more hydroxide is produced than hydrogen, then it's a base, okay? And bases are really easy to name. LiOH, lithium hydroxide, barium hydroxide. If it has OH, there's only one base that we talk about a lot in bases that isn't an OH, and is the second part, and that's ammonia, NH3. It's a weak base, and it has many of the same properties, okay? Okay, and the next guy was a guy by the name of Bronsted, okay? And what he worked with is he talked about when you're moving things around, when you dissolve something in water, when you're moving around, and he said, so when he talked about acids, he said they're proton donors. He considered hydrogen, H plus, as a proton. And so if you donate them, if you give them away, because again, if you take away one, you're going to end up with a positive charge. That's a proton donor. Okay. And then he said a base is a proton acceptor. Okay. Which makes sense because H plus would be your hydrogen. An acid is H plus, it's positive. And then a base is OH and it's a negative. Okay. There was also the Lewis, I didn't put those in there. Really, the definition I'm going to deal with is the Arrhenius, hydrogen, or hydroxide. But here's what happens, okay? So here's your water, okay? When the hydrogen ion is formed in water, okay? So what happens if you look here, here's water. If it breaks down, when you add it to solution, if you end up with more of these guys, and actually what they'll do is hydrogen will attach to another water and they produce something called HO, it's H3O, it's called hydronium. And really, they say, like Arrhenius said, it was the hydrogen, but it's really the hydronium, which is water plus one hydrogen. Okay, this is what it looks like. So when you take something and you dissolve it in water and it starts to form these hydronium ions, water plus one more hydrogen, that's an acid, okay? So they'll break down here. And again, if you get the hydrogen breaking off of the water and adding itself to a different water molecule, you end up with H3O, and that is hydronium. It has a plus one charge, okay? It's a positive charge, and that's what makes solutions give them their acidic properties, okay? If you're looking at your Bronsted Lowry, again, that's where you're talking about the protons. Okay, if you look at this equation right here, okay, I'm going to take HCl, hydrogen chloride. Okay, well, when you write it like this as a gas, when it becomes in solution, HCl is hydrochloric acid, which you've probably heard of. We talk about hydrochloric acid. And again, how do I know it's an acid? Oh, what? H is listed first. Okay, I put it with water. Okay, and I end up with chlorine because what happens is the H drops off here and joins with here. So the H goes to here, and that's where I get my hydronium. This is how I know this is an acid. okay, because I get this. All right. So when you're looking at this, they have something called conjugate acids and conjugate bases. And I'll talk more about it here. But here's my acid. Here's my base. Okay, the one that loses the hydrogen is going to be my conjugate base. And the one that gains the hydrogen is going to be my conjugate acid. So this is a conjugate base, this is a conjugate acid. And again, I'll show you some more here in a minute. Okay. Okay, when you're talking about a Bronsted-Lowry acid, it has to have at least one removable. Okay, this removes one hydrogen and forms that. If you're talking about a base, okay, it must have at least one non-bonding pair of electrons to accept. So again, this would be my Bronsted base because it accepted one hydrogen from over here. Okay, so when you're dealing with water, water is crazy because water can be either an acid or a base. Because remember I said if H is listed first, it's an acid, and OH is second, it's a base. Well, water's real formula is HOH, so it can be either or. They say water is amphoteric, okay? So in this case, now I started with a base, and remember I said most bases are OH, but ammonia is also considered a base. It's the only one that isn't written in the standard formula. But look what happens here. I have a base here, and when it goes over here, it gains one. Okay, so if this would have been an acid, it would have lost one, but it gained one, so that's why I know it's a base. And then in this case, when I went back here, I said my water was a base because it was reacting with an acid. Well, in this case, it's an acid because it's reacting with a base. So water will be whatever you want it to be, okay? If you react it with a base, it'll become an acid. If you react it with an acid, it'll become a base. Then over here, again, I'm adding a hydrogen. It's accepting a proton, Bronsted-Lowry. Okay, so this will become a conjugate acid. And then because water gave its hydrogen to this guy, it becomes hydroxide. And again, this is how I know this is a basic reaction. Okay, so water is unique because it can either donate a proton or it can accept a proton. If it donates a proton, like it did here, it becomes a base. If it accepts a proton, sorry, I have to whip back here, like it did here, here's water, and then I added a proton to it, then it's an acid. Okay, so like I said, water is unique in that way. It can do either. And that's why they call water amphoteric. So when we're doing these equations, we're going to react an acid with a base. Water, you have to look at what it's reacting with. If it's reacting with a base, it's an acid. If it's reacting with an acid, it's a base. And so water is amphoteric, okay? So when I was talking about conjugate acids and bases, okay, when you're looking at your formulas, when they differ by a hydrogen, they're a conjugate acid-base pair. So here's what I was saying. If you remove a hydrogen, like here, we got HNO2. This would be nitrous acid, okay? I'm going to give you a list of all the acids. I'm not going to give you an assignment with the names of acids, but I'm going to give you a sheet that tells you all their names so you don't get confused if you see them. Okay, but anyway, I remove a hydrogen, becomes NO2. And again, think of hydrogen as a proton, okay, because that's really what it is. So we put it over here. Now this is the acid. This is its conjugate base. I remove the hydrogen from here. Now water, because I'm reacting with an acid, is a base. Okay, now I'm adding a hydrogen to this. Okay, so I'm going from H2O to H3O, and now it has a positive charge because I added one proton. Okay, so the base now, add a hydrogen to it. Now this is my conjugate acid. So when you remove a hydrogen from an acid, it becomes a conjugate base. When you add a hydrogen to a base, it becomes its conjugate acid. And that's how you figure out conjugate acid-base pairs. Anytime you have an acid-base reaction, you have this going on. Okay, reaction between acids and bases always yield a conjugate base and a conjugate acid. In this case, I know if I tested this, this is going to be acidic solution because I got this guy right here. Okay, see how I don't have any OH? So I know this is an acidic. Okay, how do we test that? I got to check the time here. We're good. Okay, we can use pH scales. We can use all kinds of things to figure these out. But if you look here, here's to tell you the strength. And really, they measure strength not by if it eats your skin faster, than, you know, other stuff. What they do to measure the strength of acids and bases is how well do they break apart. Okay, when you mix them with water, do they form a bunch of hydrogen, or do they kind of hang together and just form a few? That's what they determine their strength by. And if you look on this chart, we have many. HCl is hydrochloric acid, sulfuric acid, nitric acid. These are your three strongest acids. Okay, we actually have hydronium in there, and then we have some, these are all weak acids, but most of these have a hydrogen removed from them already. And these guys down here, well, OH wouldn't have any acidic properties because it's actually a base. So if we go over here, we start with the strong bases down here. And the reason why it's opposite, okay, strong acids, strong bases, they're going to be opposite of each other. Weaks in the middle, and then they're going to be opposite of each other, okay? And if they're using this scale like as a pH scale, we'll talk more about that in a minute, the low numbers are here and the high numbers are down here. And I'll tell you why that is as well. Okay, so here we've got our strong bases. We've got CH3 here. Okay, these are their base, the base when you have the conjugate, okay? All right, so, excuse me, acids above the line, okay? They're strong acids and their conjugate bases, excuse me, do not act as acids in water. So in other words, if you have a strong acid, its conjugate base is going to be weak. If you have a weak acid, its conjugate base is going to be strong. I guess this is kind of a more complicated way of saying that. Okay, but substances between the lines in the water are conjugate acid-base pairs. So if you have an acid-base pair, and again, remember when you're talking about an acid, you remove a hydrogen, that's its conjugate base. If you're talking about a base, you add a hydrogen, that's its conjugate acid. So that's acid-base pairs. And whenever you have a reaction, that happens. So if you have a strong acid, it's going to produce a weak conjugate base. And you can see them there go across from each other. See how HCl, now we got Cl. I removed a hydrogen. This is its conjugate base. This is strong, this is weak, or barely even, you know, basic. So that's how these go across from each other. Okay? So again, when you're trying to figure that out, all you have to do is remember when you're doing your acid-base pairs, hydrogen take away, acid take away a hydrogen, you got your conjugate base. If you have a base, add a hydrogen and you got your conjugate acid. Okay? So remember we talked about water, and water is amphoteric. The thing about water, as it sits, it will self-ionize. It will start to break down into these guys. So we've got water and we end up with one OH and one H3O. And this, you don't have to do anything to it. It will happen. If you check like distilled water, when you first, you know, get the distilled water, it'll have a, you know, it'll be right neutral. But as it sits, it actually will become a little acidic, and that's because it absorbs carbon dioxide from the air. It'll just start reacting with whatever's wrong with it. Because water's pretty dynamic. It's always moving, okay? Okay, so in pure water, few molecules are going to act like acids and few will act bases, but they will self-ionize, okay? But now if I add something to it, I can move this process along, okay? If I add HCl to this, now I'll make it very acidic. If I add sodium hydroxide to it, I'll make it very basic. So I can, you know, it's starting to do this by itself, but you can move the process along by adding a solute to it, okay? Okay, so I'm going to quit there because then I'm going to start talking about how you can determine these numbers, okay? How you can determine by looking at what they call the pH, which I'm sure you guys have heard of before, and how you determine that. So we'll quit right there.